you all remember that if you had d dx, because we just did this, of e to the x, that equals e to the x. And if it was a chain, then it's still e to the u. You just have to multiply it times the derivative of u. That's what we did in 5.4. So 5.5 adds in another layer. What if it is not e? So the new portion to this is if it was d dx of any base a, then it would equal a to the x times the natural log of a. Now, if it wasn't x and it was u, we do the same thing. It's just going to be a to the x, a to the u times the natural log of a times the derivative of u, because this last piece over here is just that part of the chain rule. And you only chain if you have something in the exponent that the derivative is equal to something other than 1. All right, so let's go ahead and do 2 examples with this, and I'll leave those rules up there as I'm doing it. So if I go ahead and have y is equal to 7 to the 2x minus 1, the derivative of that, first part stays the same. So that is 7 to the 2x minus 1. Now I multiply that times the natural log of whatever the base is. In this case, the base is 7. So that's going to be the natural log of 7. And then the next one is the chain. So therefore, then I go ahead and multiply that times 2. So therefore, the derivative is just equal to 2 natural log of 7 times 7 to the 2x minus 1. Now, I will go ahead and take it this way, but I don't think this is the way your book would leave it. And I want to go ahead and make sure I go over the rules of exponents with you here for a second, because it's really important. If I go ahead and look back, if I had 7 to the a times 7 to the b, that would equal 7 to the a plus b. So I could actually change the way I'm doing this, and I can go ahead and break this apart. And if I did that, that would equal to 2 natural log of 7 times 7 to the 2x times 7 to the negative 1 power, which gives me the fact that this would then be 2/7 times the natural log of 7 times 7 to the 2x. I'm not quite sure the way your book would write that. They may write it either way. This requires a quotient rule, right? Yes. All right, so let's go ahead and write that out. So if I let u equal to 3 to the 2x, then the derivative of that is equal to 3 to the 2x times the natural log of 3 times 2. And again, this is, the first part stays the same. Then it's the natural log of whatever that base was times the chain rule. X is nice and simple. V is just x. The derivative of that is just 1. Sorry, I didn't have room to go ahead and do it the way I normally do, as far as making sure I can cross the products to see them. But now I can go ahead and do these. Remember, when you're using the chain rule, it is always the derivative of the numerator first. So then that gives me 2x times the natural log of 3. And I just like putting them in parentheses because I do. It helps me see that all of those are 3 separate terms inside there. Minus 3 to the 2x all over x squared. The nice part about the logs is you do have the ability to separate them. You can make some of these log problems a lot more difficult. And we did those in the first section when we did this. So log base 2 of x squared plus 7 to the 3rd power. You could go through and do this and take the derivative and make all of this u. That's not a problem. However, a more efficient way to do that is to go ahead and take that 3 and pull it out front of there, leaving you with g of x is equal to, that 3 stays the same. Now we're going to break this up the same way. The first thing we're going to have, this is 1 over x squared plus 7. Then the next piece that I have is I have to multiply that times 1 over the natural log of 2. And then the last piece, I'm going to have to do this with, I need to chain. And that chain rule here is just times 2x. So I have g of x is equal to 6x over the natural log of 2 times x squared plus 7. It's always 1 over the inside term times the natural log of whatever the base is, and then the chain rule if you need it. All right, let's go ahead and do one more. Let's make that y is equal to the log of x squared minus 1 all over x, which gives me the log of x squared minus 1 minus the log of x. Now you can do it this way if you want, but I do want to show you the fact that we can still expand this more, because this is the same thing as saying x plus 1 times x minus 1. That's the difference of 2 squares. So if I do that, I can expand it some more and make it equal the log of x plus 1 times and the times turns into a plus the log of x minus 1 minus the log of x. If you don't expand at all, you're going to have a slightly different answer. You can make the answers the same by finding the common denominator, but again, that's not going to be required. So now I have y prime is equal to 1 again, it's always 1 over whatever this argument here is. Now, this does not have a base that's written, but you'll hopefully remember that anytime there's not a base that is written, that 10 is the base of the log. So this becomes 1 over x plus 1 times the natural log of 10 plus 1 over x minus 1 times the natural log of 10 minus 1 over x times the natural log of. But they were only for dx of a to the u, right? So when you're using the term a is a constant, not a variable. So this one's tricky. I can't do that same way because then I wouldn't be taking the derivative of the base. So the way you have to do this is you have to change the form here. And the way I want to do that is I want to do that by taking the natural log of both sides. Could I use any base? Yes, but just in our life, if I use a natural log, it just makes things a lot easier. So now I have the natural log of y is equal to the natural log of x to x minus the x minus 1 power. We want to go ahead and expand this and bring that x minus 1 out front. So now I have the natural log of y is equal to x minus 1 times the natural log of x. And I can't take the derivative, well, I could, but I really don't want to use the product rule. So I want to go ahead and expand this. You could if you want to use a product rule. That will give me the natural log of y is equal to x times the natural log of x minus the natural log of x. I just distributed, yep. I'm still going to have to use a product rule, but it just makes it easier to do this when I use the product rule between x and the ln of x. That's the natural log of y, correct? So because that's the natural log of y, am I going to have to use implicit differentiation with that? All right, so I'm going to need to use implicit differentiation, and here I'm going to have to use the chain rule. Excuse me, not the chain rule, product rule. So for the product rule here, I have x, the derivative of x is 1. Then I have the natural log of x, the derivative of the natural log of x is 1 over x. So coming back up here, the derivative of the natural log of y, that gives me 1 over y times dy dx is equal to, now when I use a product rule, I need this piece and this piece, but x times 1 over x, that's just equal to 1. So over here on this side, I have 1 plus the natural log of x minus 1 over x. We don't want to leave it this way. I would like to have my answer all in terms of x's. So we're going to do a little substitution here. If I go back to the beginning, if you recall, y was equal to x to the x minus 1 power. So instead of having 1 over y, I'm going to go ahead and say that is 1 over x times x minus 1. So basically I'm going to multiply both sides of that times x minus 1. And all of this gets multiplied times x to the x minus 1. So dy dx, or y prime, however you guys like to write it, it does not matter to me, is all going to equal to x times x minus 1 times 1 plus the natural log of x minus 1 over x.